Alright, so today we're going to talk about logarithms. We're going to talk about what they are, we're going to talk about notation, we're going to talk about viruses, and I even have a special message from our sponsors at Blammo. Yeah, if you haven't figured out, Blammo's actually not a real thing. It was actually fake commercials that they had during the Ren and Stimpy show when I was a kid. Let me tell you this right now, my parents didn't like me watching it at the time. I liked it, but now watching those things as an adult, I realized something. Those people were on drugs. Today, what are we talking about? Logs. Everybody loves a log. Everybody wants a log. They're really fun. Let's have some fun, okay? I promise it's gonna be fun. I'm going to start off with a practical example. We're going to look at the growth of a novel virus, which is a bit topical in 2020. Let's assume that on day 0 we're going to have 1 infection, and then we're going to have a growth rate that increases by a factor of 2, or doubling in normal speak. On day 1 we will have 2 new infections. On day 2 we will have 4 new infections. On day 3, we'll have 8 new infections, and this is going to continue to increase every single day, where we're going to have 2 times more new cases than in the previous day. Alright, now we can take this growth rate and put it into a table, and then we can form a rule for that table, and we can say that after n days, the number of new infections would be 2 to the power of n. So how many new cases will we have after a week? And how many new cases could we expect to have after a month? Well, using our rule, what we can do is we can plug the number in. So after a week, that's 7 days. So we say 2 to the power of 7 is 128. So that would be 128 new infections on day 7. Now, it's for 1 month, we'll put in 30 days. And we can see here that after 30 days, there will be 1,073,741,824 new cases on that day. Exponential expressions grow rapidly. Of course, in this model, we are assuming that the virus will spread at a rate which doubles every day, but in real life context, that's not necessarily how things work. It's much more complex than that. So what we're going to do right now is we're going to flip this question right around and look at it in a sort of backwards sort of way. How many days would have to pass before we would have 16 new cases? So if you can see, this is a bit backwards than the way that we were asking it before. Let's have a look. Well, we'll write it like this, where we have a rule, and it's 2 to the power of n is equal to 16. So this is basically saying, how many days will it be before we have 16 new cases? Well, the numbers are quite simple, so we're going to have a look at 2's, and so how many 2's do we have to multiply together to get to 16? Well, I can see here it's 4 2's, so we can say that after 4 days there will be 16 new infections. So I just want to try and make this as simple as possible. What we just did was a logarithm. We went backwards. We had the final answer, which was 16 new cases. We knew the growth rate, which was 2, and we were asked to say, well, how many days would it be? So what we had to do in this problem was find the exponent rather than the answer. That is a logarithm. So, I mean, the first one here you've seen in previous years, but the second one sort of flips the question right around, and we're looking at it from a different perspective. I think it's really important that we just, at this point, make it very clear that a logarithm is the same as an exponential pattern, but it's just looking at it from a different perspective. Let's look at some notation for logarithms, and I will focus your attention on the details of this different perspective. Alright, so here is our exponential on the left side, and here is our logarithm on the right side. Here are the bases, or growth rate, of the exponential expression, and where it is in the logarithm. Here is the index, or exponent, and here is where it is in the logarithm. And here is the final result of the exponential, which is the argument of the logarithm. I drew this to show how this information interrelates and how we just shuffled the numbers around to answer different questions. Upon reflection, it could be more confusing than helpful, but I don't know, some people like these sorts of things. Let's talk them out in words. Okay, so on the left side, I'll start there, and then I'll go to the right side. Left side, 2 to the power of 4 equals what? Now on the right side, 16 equals 2 to the power of what? Now finally, this is how I would read this mathematical sentence. Log base 4 of 64 equals 3. The base is 4, the argument is 64, and the answer is 3. Now really quickly before I go, I want to come back to this problem that we had with the novel virus. And I'm going to show you how we can use this logarithm to solve what could be a potentially complicated problem. So have a read. If a novel virus were to uncontrollably double in the number of infections each day, on what day would the total number of new cases be the same as New Zealand's population? Well, a little bit of digging around, you can find that New Zealand's population is approximately 4,818,000. And if we were to do log base 2 of that number, we would get 22.2. So what does that mean? It means that after a little bit more than 22 days, the number of new cases would be the same as New Zealand's entire population. This is how you can use logs for some of these harder contextual problems. I hope that you found this lesson helpful, and we will be looking more about logs in the next couple of lessons. Thanks for watching, and I hope it helped.
Everyone wants a log. You're gonna love it, log. Come on and get your log. Everyone needs a log.
Log from Blammo.